Okay. So what we have done is the following. So as I said earlier, our aim is to prove the following theorem. The theorem is if you have a universal set X, if you have a set X, maybe I will make corrections here. If you have a set X, okay, then if you have an algebra of subsets of X and you have a sigma additive function, a function which is sigma countably additive on this algebra a function mu, then you can extend that function to a unique measure. You have to prove uniqueness. We have to prove the existence. Then we have to prove the uniqueness of the measure, which we can extend to the sigma algebra generated by A. That's okay. So that it's an extension. So that it's restricted to the algebra is mu. Okay. So towards that goal, we have defined something called an outer measure, which is defined on all subsets of X, which is defined on the power set of X. So which is defined here, which is mu star is from, mu star is from power set of X to 0 infinity, which is defined as infimum over all collections, infimum over all collection which cover X, countable collection which cover E, okay, countable collection which cover E, where with sets in the algebra A. Okay, sets in algebra A which covers that. So because they are in the sets in the algebra A, mu is defined for that. And then you take the infimum over the summation, n equal to 1 to infinity mu of A. You take the infimum over this collection. Then we proved that the mu star restricted to that A is mu itself. And mu star is monotone, which is just an easy observation. That is, if E is contained in F, then mu star E is less than or equal to mu star F. So then the third thing we proved is, third thing is mu star is subadditive. Okay, if you have a countable collection, then if E can be written as a countable union of En, then mu star E is less than or equal to mu star of summation mu star of En. So that also we have proved. Then we proved that, that we have already, I have said it earlier, so I have repeated it. So maybe I will erase this. So this I have already again written that its restriction is okay. So now we want to define a sigma algebra. We want to define a collection of set, okay, and which our plan is to prove that forms a sigma algebra, and that sigma algebra will contain A. So that's also we want to prove. So once we prove that, then we have already proved that we would have proved that the mu is extended to a bigger sigma algebra containing that script A, the algebra. Okay. So as I said, I'm feeling that I'm talking to myself. So if some videos are on, it will be helpful. And I tell you that I will not reduce any marks if you don't switch on something. But if there is some interaction, then if there is some good interaction, then I may give marks to that particular person, the extra marks or something. If there is some good interaction, good questions, and all those things. Okay. So then otherwise when I talk to somebody, then I remember something what to talk next, another thing. So I'm getting absent. I forget.
Okay. I have a question.
Yeah, you ask. Yeah.
Yeah. So, is the restriction of this outer measure to the sigma of A, is that the mu bar we are looking for?
Say it again. I'm sorry, I didn't hear.
So, if we restrict mu star to the sigma algebra generated by A, is that the mu bar we are looking for?
Excuse me, but your voice is breaking too much. I cannot understand.
You want to ask about the sigma algebra generated by A? What are you asking precisely?
So I am asking that about the mu bar.
Can you? I didn't really hear. No, it's some very jarring in the end. Others. I have defined a sigma algebra A, sigma algebra M, which we have to prove that it's a sigma algebra. Okay, you are asking something about sigma algebra generated by A. What is that precisely?
Sir,
So will that mu bar be same as that of the restriction of mu star? Yeah, that's what. So we will, yeah, see, we have defined mu star because that is defined on all subsets. It's all the same thing. Then we restrict that mu star to the sigma algebra generated by A. So that is what mu bar is. Correct. Correct. There is only one object we have. We have mu. And that mu we extend to mu star. Okay, that we have proved already. Then we will restrict that mu star to our sigma algebra, and that will be called as our mu bar. So this is just a notation because it's defined on different sets. We want to call that, consider that as a different function. Okay, so that's all. Okay. So
sir, what is the GPA requirement for second year students to get this course?
what is the GP? What is it?
Like what is the prerequisites for second year students to create this course? Like, are there any GPA requirement or anything?
No, I don't. Anybody can attend. I don't even understand.
Anybody can create this course.
Yeah, anybody can take this. I mean, I don't have any problem with that. If there is any problem, you ask Rajeshwari, Manoj, and all those people. Anybody can attend this question. If you can take it for grade, register, so you can. I said, what is the if you can understand this course, anybody can take it. Okay, I have no problem with that.
Okay, sure.
So you have to check CMI rules. I don't have any rules. Okay.
Okay. Right.
Okay. So my only rule is you are supposed to attend this question. That's all. Okay. Sorry, understand this. Not understand this course. That's all. Okay. So.
And sir, you did not send the lecture note of the previous class.
I couldn't send. That's the problem. I mean, I don't know my laptop. When I tried to attach in my mail, it is not recognizing. I mean, it's not showing this folder. I don't know how to sort it out. Okay. This folder is not at all visible when I check for attachment. It's showing other folders. It is. I mean, there is something folder called notes where this is saved. It's not showing that folder. I don't know how to sort it out. Okay, maybe we can check it here itself since I can share your screen. If you can help me, we'll do it later in the class or something. That's why I couldn't send. Okay, but anyway, it's in the video. You can look at the video. Yeah. Okay, when am I able to send? I will send you. Okay, it is just I was not able to send. Okay. So towards that goal of defining, extending to the sigma algebra, we define the following. So we call a set A to be mu star measurable if mu star A satisfies this condition, which you have defined earlier. It's defined in the last class. Mu star E equal to mu star A intersection E plus mu star A complement intersection E for all E. So if this statement is, if this equation is satisfied for all A, then it is called measurable. So first we want to prove that. So then we denote this collection by script m mu underscore and underscript mu. So we want to first prove that this algebra is contained in. So we want to prove two things. So we want to prove that this collection is a sigma algebra. We'll prove it later. Before that, we want to prove that this script A, our algebra A, is contained in that. Okay. So towards proving that, so what is it we have to prove? To prove that the algebra is contained in that. So we take a set A in script A, and we take something like that. Then we have to. So there is an observation we made earlier. So we in the previous class, not yesterday, in the previous class, the observation. So that is thanks to, and writing it here, I hope it's visible. So maybe I can insert a space here. Yeah. So thanks to the subadditivity we have proved, we have proved a subadditivity for this mu star. So it is enough to prove measurability, maybe. To prove measurability of a subset A, P of X, it is enough to prove mu star E is greater than or equal to mu star A intersection E plus mu star of A complement intersection E. So we have to prove it's equal, but some subadditivity implies the other inequality. So we only have to prove this, okay, for all E. Okay, that's what we have to prove. So it's enough to prove this inequality. So that's what we will do here. So we want to prove that we take any subset E and we want to prove that mu star E satisfies, and we take a element A in script A and we want to prove that inequality. So how do we prove that? So we know that we have to prove that mu star E is greater than or equal to something. That's what we want to prove. Okay. So mu star E is defined as infimum of some collection. Okay. So we know that I explained it in the last class. Infimum means what the definition of infimum is, given epsilon greater than 0, if we increase that number mu star E by epsilon, then we will find a collection between mu star E and mu star E plus epsilon. Okay, so the statement is the following: there exists a AN collection AN. Okay, given epsilon greater than 0. Given epsilon greater than 0, there exists a AN such that mu star E plus epsilon is greater than or equal to summation n equal to 1 to infinity A mu of A. Correct? Okay. So that's the definition of infimum. Mu star E is defined as infimum of some collection. By the definition of infimum, this is true. Okay. Now we know that mu is a sigma additive function. So A and A complement are disjoint. In particular, AN intersection A and AN intersection A complement are disjoint. Okay. I'm sorry, I'm trying it. Very difficult to write it. Are disjoint. So this implies this is greater than or equal to. So this is equal to. That one is this. This one is equal to summation n equal to 1 to infinity mu of AN intersection A plus mu of AN intersection A complement. And of course, that is equal to mu of A. It is equal to, no. Yeah, then this, so then we also have E intersection A is contained in union n equal to. So here, there exists AN such that I forgot to write E is contained in union of AN. Okay. Such that E contained in n equal to 1 to infinity is contained in AN intersection A. Similarly, E intersection A complement is contained in AN union n equal to infinity union AN intersection A complement. So these things implies that this is, so since, so then because of that, this is greater than or equal to mu star of E intersection A, and that is greater than mu star of E intersection A complement. Okay. Okay. So we have proved it. So we have just proved that mu star of E is greater than or equal to mu star of E intersection A plus mu star of E intersection A complement. That's what we want to prove. Okay. So this implies A is contained in. Okay. This is very easy. Is that clear? This is true for all the epsilon. I'm sorry. This is true for all epsilon. So I forgot the epsilon. Here is an epsilon here. Okay. So since this inequality, so this is just an inequality. Was to mu star E plus epsilon is greater than 10. Since true for all epsilon greater than 0. Okay. Maybe I should leave some space. Okay. So since that inequality is true for all epsilon greater than 0, we get this inequality. Okay. This is the, so that implies A is contained in that. Okay. So I think it's fine. Okay. Maybe I didn't write it properly. It's a, but everything is written here. Okay. All the argument is written. Okay. So we have proved that this A contains this. Okay. So then now we want to restrict our mu star to this mu. Okay. Once we restrict this to mu, then we will we have to prove that mu is a sigma algebra. So that is the next proposition. Algebra and additive. Okay. So okay. So assume that this proposition is proved. Now we have a theorem. I said there is a theorem. If you want, we call this theorem as something. Theorem star. Okay. So if we call the theorem a star, so assuming theorem star, assuming the proposition, assuming the following. If you assume this proposition, then the theorem is proved. So the proposition says that this mu, what is a collection of all measurable sets that form a sigma algebra. Then we want, and another statement is mu star restricted to that mu is sigma additive. Then I am claiming that the theorem is proved. So the theorem says that, so that's just clear, since A is contained in mu, so A is contained in mu, this implies sigma A is contained in mu, okay? Because mu is a sigma algebra, so sigma that is sigma A is contained in that. So let mu bar equal to mu star restricted to the sigma of A. Okay. Then this gives, so then we have proved everything. So it's just clear. We have proved that this is a sigma additive function. That's what it means. So this implies sigma is a measure. It's a measure on a bigger sigma algebra. It's a measure on sigma of A. So that's true. Now we want to prove that it's unique. Okay. So only uniqueness has to be proved.
So you mean mu bar is the measure, right?
Mu bar is the measure, right?
On sigma A?
Mu bar is a measure, okay? And it is the measure, if you want to say. Okay, it's a unique measure, if you want to say. So to prove uniqueness, so consider this. So I consider a new object called like this, equal to. So no, I want to say something more, sorry. So I want to prove it's unique. So suppose there exists mu1, mu2 on sigma of A, satisfying mu1 restricted to A equal to mu equal to mu2 restricted to A. Okay, suppose there exists two extension. I want to say that mu1 equal to mu2. Okay, so suppose there exists two extension, then I want to say it's equal. So then define. So let equal to all those A in the sigma algebra generated by A, such that mu1 of A equal to mu2 of A.
Sir?
Yes.
Sir, by the way, have you proved the proposition m of mu is a sigma algebra?
I'm saying that once the proposition is proved, I'm saying that the theorem is proved. Okay, the theorem is in the top. You want to see the theorem? The theorem says there exists an extension to the sigma algebra generated by A. So that is clear. Maybe you want to prove, I mean, which is convenient for you. I will prove the theorem and then come back to the proof of proposition. Okay. The proposition says mu is a sigma algebra and mu star restricted to mu is sigma additive. Okay, that's the That's the proposition. Once this proposition is proved, I'm saying the theorem is proved. Maybe I should have proved the proposition and then come to the theorem. Whichever is okay. I'm proving the theorem now. In the theorem says that there exists an extension of this mu, which is mu bar, and which the extension is unique. I mean, we get an extension just by restricting mu star to sigma algebra generated by A. And then we want to prove that it's uniqueness. So I'm just proving the uniqueness now. Okay. Okay. I haven't proved the proposition. I will prove proposition. Okay, which is long. So before that, I'm proving the theorem.
Sir, also please scroll up a bit. Sir,
Yeah.
can you please scroll up a bit?
Show what? The theorem.
Yeah, the proposition.
Proposition. Okay. Yeah, the proposition says that mu, I'm sorry, mu is sigma algebra, and when you restrict mu star to mu, it is sigma additive, countably additive. That's all.
Thank you, sir.
Which is long. The proof is long, so that's why I want to first prove that the easy thing, which is that this is there exists a unique extension. Okay. So I want to prove, I mean, it's clear. Once the proposition is proved, it's clear that there exists an extension of this mu to the sigma algebra generated by A. Okay. We want to prove that that extension is unique. So for that, we have to prove that mu1 is equal to mu2. Now then we apply the standard idea, which we have already used, I think. So the standard idea is you take the collection of all subsets where this mu1 and mu2 coincide. Of course, they coincide on the algebra itself. Okay. So you take the algebra, which is internet connection is not stable, it says. So if you get, I mean, I hope it's not interrupted. So we want to, we know that it coincides on mu because both are coincides on A because both are extension of mu. Now we want to say that it's coincides on the sigma algebra generated by that. For that, we take this collection where it coincides. Okay, then A is contained in this, and we want to prove that this. So, and it's enough to prove that, and it contains the sigma algebra generated by A. So it is enough to prove E is a sigma algebra. Okay. So that's what we want to prove. So we want to prove this is a sigma algebra. So, right. So to prove that this is a sigma algebra, that's what we want to prove. Enough to prove E is a monotone class. Okay, by the Halmos theorem. I mean, I said Halmos theorem, it's also called monotone class theorem by, which we proved in the last class, monotone class theorem, which is also called as Halmos theorem, which is due to Halmos. Okay. So we have to prove it's a monotone class. So from that, it's very easy to prove. So why is it true? So suppose so then we want to prove, suppose AN is a collection which increases and it increases to A, then we want to prove A is also there. Okay. So then the AN is in this implies mu1 of AN equal to mu2 of AN. Okay. Then what happens? Then if, so then since that increases to that, sorry. Right. So, but now both mu1 and mu2 are measured. Okay. Since mu1 and mu2 are measures, that's what we have assumed. Okay. Mu1 of AN increases to mu1 of This is mu1 of an increases to mu1 of a, and the same thing is also so increases from this side, mute, and also mu2 of an increases to mu2 of a. But since these two are equal, mu1 of an equal to equal, so it's maybe okay. Okay, so this implies A is, and that's the definition of this. Okay, our definition of sigma algebra is mu1 all A such that mu1 of A equal to mu2 of A. So this is there. Now to prove the other way, now we want to prove, for all Bn containing here and Bn decreases to B, then B is in this. To prove this, we first assumed it. So I made a mistake in the statement of the theorem. I'm sorry, you have to change that. There is a mistake in the statement of the theorem. We have to assume that this is sigma finite measure. Okay, this mu is sigma finite. I defined what is called sigma finite. Okay, so mu be a sigma additive. So mu has to be assumed to be sigma finite. So I will define what is sigma finite. We defined sigma finite in the very first class, if you remember. I will define it again. I mean, in the course of this proof, I will recall what is sigma finite. So to prove the other way, we have proved that increasing. Our aim is to prove that the script E, whatever we have defined, is a sigma algebra. To prove that it is enough to prove it's a monotone class. So we want to prove that it is closed under increasing union and decreasing intersection. We have proved it's closed under increasing union. We want to prove it's closed under a decreasing intersection. But then for the statement to be true, we have to assume that it's finite. So first assume our original x. So the x is in the algebra, so mu is defined on the algebra. Mu of x is finite. Okay. Then we will relax this. Then we will assume sigma finiteness and prove that. Okay, mu of x is finite. So then it's clear that then if we assume this, then mu1 of Bn decreases to the same idea, mu of B, mu1 of B, and mu2 of Bn decreases to mu2 of B. Okay, and these two are equal because they are in the Bn is in A. Okay, since Bn is in E, this is equal. They are equal. Okay, so this is also equal. Okay, so that is proved. So when it is finite, that is proved. Okay, so now we want to assume. I mean, it's same as the increasing intersection, so I am not going through the argument. Okay, it's same as the increasing intersection. So now assume sigma finite. What does it mean by mu is sigma finite? There exist An in A. I mean sigma finite from A. Okay, there exists An such that mu of An is finite and An union of An n equal to 1 to infinity, union of An equal to x. Okay, so mu of x may not be finite, but there exists a countable collection whose union is x, and each of them has finite measure. So without loss of generality, by taking, I mean, if you can take, you can redefine Bn to be union of sets up to then. So without loss of generality, when I write WLG, it means without loss of generality. We may assume An is increasing. An increases to x. Okay. 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 Then mu1 of An increases to mu of x. Whatever, whether it is infinity or whatever, this sentence makes sense. And mu2 of an increases to mu of x. Okay. Indeed, for all so by the earlier okay, now we want to prove that decreasing union in the all we are doing all these things to prove that this whatever the script E, this is closed under oh no. Yeah, we are working to prove that this E is a script E is a sigma algebra. So it's closed under decreasing intersection. That's what we want to prove. Okay. Oh, there is, this is, maybe I should have changed, since I am using A and B for something else, maybe you can change this to xn or something, if you don't mind. I change this A to x, just to be clear. Okay. Okay, now it's clear.
So the increasing case remains the same, right? The proof remains the same.
Yeah. This is not the increasing case. And we are
Like-
still doing the decreasing case. For that, we are assuming the whole set X, the universal set X, can be written as some increasing union of Xn. Now we will restrict our measure to Xn. Okay. There, this mu and bar coincides. Okay. We will prove that this coincides on that. Okay. Now suppose. Okay, I assume suppose all these bn's are contained in some xn or something, okay, for some xn, or maybe you just notice the following. Maybe this is not needed. Notice for all,
Sir,
yeah.
sir, here, like, have you written there exists n belongs to a mu of xn less than infinity?
Yeah. Mu of xn less than infinity. What is less than infinity?
Yeah, so just before that, what have you written?
No,
Like mu of xn less than infinity.
No, I am saying the following. We want to prove that our E is monotone class, which is we have proved that it's closed under increasing union. We want to prove that it is closed under decreasing intersection. We are through if the measure is finite. Okay. Now we are assuming the measure is sigma finite. So for it to be sigma finite means there exists xn which increases to x such that mu of xn is finite. Okay. Now for any E, maybe any A, any A, mu of A equal to supremum or the limit or whatever, supremum of mu of A intersection xn. Okay, that is clear by earlier whatever we have observed. Okay, right? So then this A intersection xn is finite. Okay? Because A intersection xn will increase to A. Because of that, mu of A equal to supremum of mu of that. Okay. Now, for all Bn, which decreases to B, okay, with Bn in E, okay, okay, if mu1 of by the earlier argument, mu1 of B intersection xn. Sorry, this is xn. I'm getting confused. Xn equal to mu2 B intersection xn, right? By the earlier argument, because mu intersection B intersection xn is a finite, the whole set is finite. Because of that, this is true. Because, I mean, if you want, I will write it. Since Bn, I'm sorry, maybe I will call it M or something. M, change it to M. Okay, for all M. Okay, maybe here also you can write it M, supremum over M. Okay, because N, since Bn intersection Xn will increase to Bn as M goes to infinity. Okay, M is fixed, N is fixed, and M goes to infinity. Okay, so mu1 of B intersection Xn is mu2 of B intersection Xn. Okay, since B intersection Xn, this coincide for all of them, so this implies mu1 of B equal to mu2 of B. This implies B is in E. Okay, so this implies E is monotone class. This implies E is a sigma algebra. That's what we want to prove. Right? So this is sigma algebra implies mu1 equal to mu2 on sigma of A. I mean, this is sigma algebra, which implies this is equal to sigma of A, because this contains A, and this contains A. So this is the sigma algebra. I mean, then this is the smallest sigma algebra containing A, because of that E equal to sigma of A. So mu1 equal to mu2 on sigma of A. Okay, so this is unique. That's what we wanted to prove. Okay, I'm just providing all the arguments. That's all. It may be boring, but I have given all the arguments. Okay, is this clear to everyone? Okay. Let me, so this is the uniqueness is proved.
So,
Yeah. Yeah. Who is asking?
so first you're taking a increasing Shayantan.
Increasing Xn. You are Sayantan. Okay. I thought you were calling the sector Sayantan.
Yeah. So first you're taking increasing Xn
Right.
such that the measure of each of them is finite,
Correct.
and then you're taking this B and intersecting them with Xn.
Correct. All
And
of
then
them.
you are-
No, you can intersect all of them with Xn. Okay. You restrict the measure to
Yes,
Xn
yes.
itself.
So you will
Okay.
have a decreasing.
Then the intersection will, you
Okay.
fix
And
a
then
Xn.
by the earlier result,
Yeah. I mean, it's clear, no? Then you take the decreasing, I mean, then the restriction, whatever the intersection, they will decrease and the measure will coincide on that, right?
yes.
No, since this is true for all Xn, the original mu1 and mu2 will coincide, right?
Yes.
Okay. Okay.
Sir, can you just once explain why we needed to do this for two separate we have to deal with the sigma finite case separately?
Yeah, because it's not true, no? The earlier we proved, in the very first class, we proved that decreasing intersection is not true for infinite measure. It's true only for finite measure, right?
Okay.
Yeah, that is not true in general. So we have to consider the finite case is clear, direct. But for sigma finite case, we have to restrict to this kind of where the measure is finite. Then you take the increasing union where this is true, right? Okay. Okay, it's because of that. So now let us go back to the proposition. The proposition is we want to prove that. So we defined a mu. We want to prove that mu is a sigma algebra. Then mu star restricted to mu is sigma algebra. Maybe I will write it again. Okay. So now the proof of the proposition. Proof of proposition. Okay. So proof of mu is a sigma algebra and mu star restricted to this mu is a measure. Okay. That means it's a sigma additive. That's what it means. Okay. Okay. So first we want to prove that it's a sigma algebra. So we will go by one. First, we prove that mu is an algebra. Okay. We want to prove it's a sigma algebra. We will prove it is an algebra. So then we will prove that it is. Sigma additive. Then we will prove that it's sigma additive. Okay. We want to prove each other. So what is the property of that? A is in mu if this is true, no? Mu star A. I mean, it's greater than, it's enough to prove greater than or equal to, which is equal to, sorry, mu star E equal to mu star A intersection E plus mu star A complement intersection E for all E and in X. Okay. So it is clear that this statement is symmetric in A and A complement. Okay. So if A is in mu, then it's clearly A complement is in mu. Okay. You just have to understand these two summations. Okay. So it's clear that it's prove that. So now we have to prove that it's closed. To prove that it's an algebra, all we have to prove that it's closed under union. So to closed under any finite, closed under finite union. To prove that by induction, we only have to prove that it's closed under two union. So we need to prove, suppose A, B are two elements in mu. Then we want to prove that A union B is there. Okay. So directly we will try this. So what do you want to prove? We want to prove that mu star E is greater than or equal to that. Okay, so mu star E, what do you have? Mu star E equal to, so we have this A intersection E plus mu star A complement intersection E. Okay, then we want to get that some something A. We want to in the place of A, we want to get A union B, and A here we want to get A intersection B. A complement intersection B complement. We want to prove this statement, whatever the statement, replacing A, we want to, whatever the statement where we have A, we want to replace with A union B. Then A complement will be replaced by A complement intersection B complement by the De Morgan's law. Okay. So, okay, so this is true. So then this is equal to, let us keep this like this, mu star A intersection E. Okay. Now A complement intersection E is another, it's just, it's another E, okay, another set like E. So, okay, so I just keep it like that. Then mu star of A complement intersection E. So, intersection B, okay, plus mu star of A complement intersection E intersection B complement. I have just used by applying instead of E in this statement, I am applying to A complement intersection E. Okay, I am applying the property for A. This is true for anything. We have assumed that B is in mu. Okay, and A complement intersection E is any set. So because of this is true. Okay. Now I take this. Okay, let us write this. Let us write this again. Mu of A intersection E plus mu star of A complement intersection. What do we have? E intersection B. Okay. Okay. Plus mu star of here I write as E intersection A union B complement. This one. Oh no. Whole complement. which I can write it like this. So now I consider this. Okay, here I have two sets, which is A intersection E. Okay, this union A complement intersection E intersection B. Okay, so you just think about it. This is nothing but E intersection A union B. Right? One second. Okay, this is clear. You just think about it. You have to prove that this is true. A intersection E, union A complement. I mean, it just, you have to get, I mean, what is E? E is equal to A intersection. E is equal to A intersection E union A intersection E complement. But then you want to get A intersection B also. Is it right?
Yeah, this is fine.
This is fine? Or is there a problem? Is it okay? Okay. So now because of this, by subadditivity, okay. So that is what we have here. Mu star of A intersection E plus, I'm replacing the union by addition, mu star of A complement intersection E intersection B is greater than or equal to mu star of E intersection A union B. Okay. Okay. So the whole thing is written. Now we have, so this thing implies, we started with mu star E, and that mu star E is greater than or equal to mu star of E intersection A union B. The rest what we have is mu star of E intersection A union B complement. Okay. So the whole thing implies A union B is in M. Okay, we have proved this. Prove the statement. Is it okay? We have to prove the property of mu by replacing A by A union B. So that's what we have done. When A and B satisfy that property, then A union B also satisfies that property. That's what it means by A union B is in mu. Okay? Is this fine?
Yeah, this is fine.
Okay,
Yes, sir.
fine to everyone. I assume that. Okay. Okay, so that is one. So then what do you want to prove? We want to, so we have to prove that it's sigma algebra. We'll come to that.
So,
Yeah.
so probably I'm missing something probably. So like don't we also need to show the other inequality as well, mu star of E?
No, I have remarked earlier, because of subadditivity, it's enough to prove this. We have proved initially that mu star is subadditive. The other way is always true.
Okay. Okay.
That is because E equal to E intersection anything union E intersection anything complement. Okay. So other thing is anyway true for any collection. It's true. Okay. So so I have remarked here. I call this as an observation or something. Okay. After defining that, we have to prove only this. So it's here. Where is it? The very observation. Maybe I will color it here. So this is the observation. Thanks to subadditivity, to prove measurability of A, we only have to prove this. Okay, it's written there, wherever I have underlined.
Sir, we should also note that empty set and whole set belong to MU, right?
That is all there in algebra A. No, A we proved A is contained in that. The algebra A contains empty set
Yes.
X, and we proved that A is contained in this. Okay, so we only have to prove this union and this. complement trivially holds. For union, we have to work out these details, which we have worked it out. Okay. Now the next thing is next claim is mu star is additive. This mu. Okay. We want to prove it's additive on this. Okay. So what does it mean by it's additive? So we have to prove that. So what does it mean by additive? Suppose we have two sets A, B, N, mu, such that A intersection B is empty. Okay, the intersection is empty. Then we want to prove that mu star of A union B, then that's what we want to do. It will follow directly, I believe, A union B. Okay, that is equal to, so what is that? Mu. So let us call this as E. Okay, if you call this as E, then apply to the property of E, then this is equal to mu star of A union B intersection A, okay, plus mu star of, I mean, we have A, B in that, and we know that A union B is also in that. That is what we have proved in the earlier claim, okay, the claim 1. Because of that, this is true. A union B intersection A complement, okay. But then this is equal to B, since, I mean, this is equal to A. A union B intersection A is A, of course, right? That's always true. A union B, if you take the intersection, that is A. A union B intersection A complement is B, since A and B are, since A intersection B is empty. Okay, because of that. Okay, so then this whole thing is equal to mu star A plus mu star B. Okay. Okay, so mu star is additive. Finitely additive. Maybe by induction, maybe I will ask. So okay. Okay, this is okay.
Yes, sir.
Okay. So the screen is fully visible, no? I see in the end. Yeah, I think it's okay. Maybe I shouldn't write in the extreme corner. Okay. Okay. Now we want to prove the third claim is mu is a sigma algebra. We have proved it's an algebra. We want to prove that it's closed under countable union. So it's a sigma algebra. That's what we want to prove. So suppose we have a AN collection AN, countable collection, which is contained in mu. All of them satisfies that mu. Okay. Then we want to prove that the union is also there. Okay. So we assume without loss of generality, since mu is an algebra, okay, we have proved that it's an algebra. Because of that, without loss of generality, AN is increasing. Okay, AN increasing. Okay. No, not AN. Sorry, I don't want that to be increasing. I want to use the property of this. So ANs are disjoint. Okay. AN intersection ANs are disjoint. Okay. Okay. So why we can assume that? That's because finite unions are there. And if you have, since it's an algebra, MU is an algebra, if A1 and A2 are there, then you can replace that A1, A2 by A1 and A2 minus A1. A2 minus A1 is A2 intersection A1 complement. And we know that it's an algebra, so the complement is there, union is there, finite union is there, because intersection is there. So because of that, okay? That's why I said, because MU is an algebra, we can assume without loss of generality, we can assume ANs are disjoint. So please verify this. This is very easy verification, which I have said it orally. I'm not writing it. Okay. And
Sir?
Yes.
So instead of, if we have a general sequence AN, we can just define a new set AN dash as AN set minus the union of A up to AJ.
Correct.
From 1 to n minus 1.
Correct. Exactly.
So that will also be in algebra, because of
it's also in the same.
So that's also in
because we have proved it's an algebra.
And
the increasing union will be same. Our aim is to prove that the increasing union is there. It will give the same increasing union. Okay. So we can replace it by a different Bn. We want to prove that. Suppose we have that, then we want to prove.
Okay.
Then we want.
Yes.
Okay. Union of An equal to infinity is in M. That's what we want to prove. Okay. It will have the same union. So. Okay. So that's what we want to prove. We want to prove that the union is there. We can arrive with that with a different union. Okay. So now let Sn equal to union of M equal to 1 to.
Sir, it's frozen.
What is frozen? Yeah, it's coming. It takes few seconds. Okay. Sn and S equal to union of N equal to 1 to infinity An. Okay. Okay. And Sn increases to S. Okay. Yeah, my internet is not very good, so that's why I'm using 2 internet. I think there is somebody else also using there. So 3 people are using the internet. That's why. Okay. So we have this. Now what do we want to prove? We want to prove is sigma additive. We want to prove that S is there. So we want to prove the following: mu star of for all E. Okay, for any E contained in X, we want to prove that the S is in the MU. Okay, that's what we want to prove. S is in MU means it has to satisfy the measurability property, which we have defined. So we want to prove mu star of E intersection S plus mu star of E intersection S complement equal to mu star of E. That's what we want to prove, right? This is what we want to prove. Want to prove this. Okay. So let us take this. This is equal to mu star of E intersection S. That's what we want to prove. So what have we proved till now? So we have proved subadditivity. So it's enough to prove. And we want to prove this because we have already observed something. So we want to prove this. Okay, we want to prove this. This is greater than or equal to this. Okay, the other way we know already because of subadditivity. Okay, so now this is equal to mu star of E intersection union of Sn n equal to 1 to infinity. I'm just writing it again and keeping this as E intersection S complement as it is. Okay. Now this is greater than, this is of course equal to intersection E. You can take the union outside, distributive property, but then using subadditivity,